Okay. Hello to everyone. I'm Pierluca Carenza from the University of Bari. I'm a PhD student, and today I will present you this paper, Reconciling hints on axion-like particles from high-energy gamma rays with stellar bounds. As you know, the coupling between axions and photons allow the phenomenon of axion-photon conversion in an external magnetic field. This can be used in the galaxy to explain the anomalous transparency of the universe to gamma rays, because photons from a source convert into an axions in the galactic magnetic field, and then it converts back into a photon, and so we observe this photon passing through a very long distance in the universe without being absorbed. This phenomenon for our galaxy is important for energies higher than the Jev scale. And then this can be also observed as a dimming of some astrophysical sources, as for instance a pulsar. In fact, in this plot, you see that the data points are the observed flux from a pulsar, and the blue line, blue solid line, is the predicted flux in the absence of axions. And so, as you see, this flux cannot explain very well the experimental data. But we can also add the hypothesis that there are axions, and then the source has an intrinsic spectrum, which is the dashed red line, and then at some point, for energies around the GeV, this flux is reduced because of the photon-to-ALP conversion in the external field. And so the flux that we observe is the solid red line. And this line explains very well, this hypothesis explains very well the experimental data. By considering a lot of pulsars and with a statistical analysis that we updated in this paper, we obtained the parameter written here for the suggested axion. And then we can consider it as a small hint in the direction of an axion. From astrophysics, we have also hints, but also bounds. Bounds comes from the active galaxies that we observe. And in this plot, you see the field regions are the bounds from two galaxies, NGC and PKS. The light green region is the old bound from NGC. Then we updated this bound with more experimental data, and in fact, this region expands to the dark green region, which is much larger. And this region can also exclude the part suggested by the hint, the pulsar hint, which is the brown hatched region, the small brown hatched region. But there are also other bounds, for instance, the bound from PKS, which is the bound in the blue regions. The difference between the light and dark blue regions is that in the light region, we are considering a very strong intra-clusters and intergalaxy magnetic field, which is of respectively of 1 microgauss and 1 nanogauss. But then, if we reduce it to a more realistic value, we obtain the dark blue region. And so you see that this bound is very relaxed. In any case, our region, the hint is not excluded by those bounds. The problem is that the horizontal line, the horizontal dashed line, which is the cast bound from solar axions, exclude completely the region of our int. Moreover, there is also another interesting phenomenon to see, that the depth transparency of the universe is explained by all the region above the orange line. So our int can also explain the TV transparency of the universe. But now, can we reconcile the pulsar int with the cast bound? And let me see how to do that. Axions are produced in the sun by a Primakov conversion. A photon interacts in the electromagnetic field of an ion in the sun, and then it converts into an axion. This flux is very well known. And now we are assuming that the coupling constant, the axion-photon coupling constant, depends on some quantities, for instance, temperature, density, or plasma frequency. And so our coupling depends on the environmental characteristics. In this plot, you see some environmental quantities of the sun, and you note that those quantities are monotonically decreasing. So we can assume in a very model-independent way that our coupling at some critical radius RC goes to 0 for the whole region inside this critical radius. So we are left only with an effective flux which comes from a more external shell of the sun. So we expect already that this flux would be at lower mean temperature, lower mean energies. The suppression of the flux in this, with this assumption is calculated as the ratio of the flux by assuming this dependence of the coupling on the environment and the standard flux. At this point, we require that the suppression factor would be enough to have a total converted flux with the coupling given by the pulsar int, and this flux that we observe in cast must be smaller than the flux with the cast bound, on the cast bound. So the suppression factor must be smaller than order 10 to the minus 2. And in this plot, you see the suppression factor as a function of the critical radius RC. And in fact, this limit of 1.3 times 10 to the minus 2 is reached for a critical radius around 0.5 solar radii. So now we assume that we have found our critical radius, but this critical radius can be given due to a dependence on the density or on the temperature or on both. So we don't know, we only know the critical radius. This is another hypothesis, the next step. So at this point, we have a new reduced flux. And in this plot, you see the axion flux from the sun, and the solid black line is the standard flux with the coupling of the cast bound. And this flux is peaked in the 27 keV region, in which we can compute the strongest bound from cast. But now our flux is not only reduced, even if we are increasing the coupling and we are using the pulsar int coupling, but this flux is also shifted to lower energies. So to obtain the same number of axions in this region 27 keV, we need to increase a lot the axion-photon coupling, reaching to a new cast bound, which is around 10 to the minus 9. So much smaller than before. But here we see that there is also a peak at energies below 2 keV. At it could be interesting to detect this peak. And in fact, CAST explored this range, the range 0.22 keV, to study solar chameleons. This was done with the grid pricks detector. But unfortunately, this detector has detected a background which is much higher than our flux, the presumed flux, the predicted flux. So there is no hope, unless the background is very strongly reduced, there is no hope to probe this scenario directly. But, well, now with the same critical radius that we have calculated before, we can assume that the coupling constant depends on the density. And then, in this case, the critical density will be of around 1 gram per centimeter cube. With this critical density, we can also, self-consistently, change the bound on HB and supernovae. So, the HB bound would be relaxed, again, because we are studying regions of the HB which are much colder than the inner part. And so the majority of the flux comes from the outer shells, and the HB bound is relaxed to 4 × 10⁻⁸. And in fact, this bound is smaller than CAST, which is the red line, and becomes much smaller than before, which was the blue dashed line. Now, also this supernova bound changed, but it disappears completely, because in a supernovae, the density is around 10 to the 14 gram per centimeter cube. So there is no hope to see an axion production from a so low density region of 1 gram per centimeter cube. So we have no more supernova bound, and the HB bound is smaller than CAST. And in this case, so we are reconciling the two, the bounds with the int. And now we can also detect directly this kind of axions in the future experiment ALPS II, which is a light shining through the wall experiment, which will start in 2021. So we don't need to wait long. And for light axions, with such coupling given by the int, we would observe a very clear signal, which is 4 orders of magnitude higher than the expected background. So we hope to detect, in this case, axions in ALPS II directly, in a completely independent way. So in conclusion, the pulsar int on the axion is in tension with the CAST bound, but we can solve this tension by assuming this dependence of the coupling on the environment. And so, solving this tension, we are also reducing the other stellar bounds. And in this scenario, which is very interesting, can also be probed directly in the nearby future by ALPS II. So stay tuned, and thanks for your attention.